Welcome back to Honors Calculus. In this video, we'll be continuing our discussion of inequalities with the idea of interval notation. In the last few videos, we've been looking at the real numbers and the basic structure that defines the real numbers. In this video, we will be investigating portions of the real numbers, which we call intervals. You are probably already familiar with the idea of intervals and interval notation from previous coursework, but just to be sure, we're going to go back through from the beginning to make sure that everyone is starting on the same page. So with that in mind, I'll go ahead and get myself out of the way, and let's jump in. A bounded interval is a set that follows one of the following four forms. We can have what's called a closed interval between A and B, which is a shorthand for the set of all x in the real numbers such that A is less than or equal to x is less than or equal to B. We can have the open interval between A and B, which is shorthand for the set of all real numbers x, such that A is strictly less than x is strictly less than B. Or we can have the mixed half-open, half-closed intervals, either open on the left and closed on the right, or closed on the left and open on the right. And just to have it as reference, that first structure is what's called a closed interval. The second one is called an open interval. Open and closed has to do with the characteristic of the endpoints. There are a lot of deeper meanings of open and closed that you may come across, depending on what future math courses you take. But these basic ideas are good enough for us for right now. We'll investigate that a little bit more when we develop some more structure of intervals later on in the course. Right. Bounded intervals are contained on the left and right side. An unbounded interval is one that is not contained on one side or the other. And when we're talking about an interval without a bound on one side, we talk about the idea of infinity as being the bound of that thing. Right, so infinity is defined as this symbol. It's kind of an 8 turned on its side. And the most important thing to remember about infinity is that infinity is not a real number. Infinity is an idea, sometimes called a transfinite number, where infinity is bigger than any real number. So infinity is defined by the property that infinity is greater than x for all x in the real numbers. And negative infinity is less than x for all x in the real numbers. Later on, when we get enough of the material to fully define what the real numbers are, we'll revisit this, and I'll try to find time to prove to you that these two definitions, even if we relax it and called it greater than or equal to and less than or equal to, would be enough to ensure that infinity is not actually a real number. But because infinity is not a real number, we cannot include infinity in an interval, which is why we use the open interval at infinity, no matter whether or not the other side is open or closed. So we can have intervals going from a to infinity, either not including a or including a, and we can have intervals going from negative infinity to b, again, either not including b or actually including b. So these intervals are called unbounded because they only have limitations on one side. But we can have intervals with limitations on even no sides. We'll get to that in just a moment. All right. So playing around a little bit with the idea of an interval, let's let I be any interval. Could be bounded, could be unbounded, could be open, could be closed, could be something in the middle. But I found two particular values of that interval that I'm going to call A and B. If you can find a third number, real number C, which happens to fall between A and B, then that means that C is in fact in the interval I. It's a little bit beyond what we're going to be looking at with intervals here, but in higher mathematics, this claim is actually taken as the definition of an interval. And from this definition, we develop the inequality meanings, the set builder notation meanings of intervals that we led off today's lesson with. So proof of that claim is possible. I'm not going to go through it just for the sake of time. I'm also not going to go through the next couple of claims in careful proof, although I do encourage you to take a look at the printed notes that go along with these videos, because the proof of these next two claims is written out there. Let's take two open intervals, AB and CD, such that C is smaller than B. And given that structure, if you take the union of the two intervals, you will get a larger interval, in this case, the interval from A to C. And if you take the intersection, you'll get kind of the smaller interval. As I said, the formal proof of these two claims is provided in the printed notes. I encourage you to take a look at it to see what it takes. But for the sake of time and energy, because honestly, the proofs don't give you a whole lot in the way of usefulness, I instead want you to think about this in terms of the graph of an interval on the number line. Right, so we have here a couple of number lines. And I know that A has to be smaller than B, C has to be smaller than D, and C also has to be smaller than B. Although I don't know for certain, I guess that in fact, that's a mistake that I made. That's why we go through proof, because it helps us make sure that we have our statements correct. I said that C is less than D, but that's not the entirety of the statement I have to make. I needed to write out the full inequality. A is less than C is less than B is less than D. Because with that, if you take a look at the interval between A and B, and you take a look at the interval between C and D, you can graphically see that if you union them, if you press them all together, you'll get everything from A to D. And if you intersect them, you try to look for where they overlap, you'll get the space between C and B. That is probably an idea that you have seen in previous mathematics coursework. Again, playing around with the inequalities like that is not really what I am so focused on today, but instead I wanted to talk about, we can solve this graphically in drawing two number lines, but if you look at the typed proof of this statement, it fills a page and a half of the written notes. So just thinking about the difference between a rough idea of how something will work and a formal proof verifying or guaranteeing that the idea will actually hold. But a consequence of that idea, if we want that to work out the way that it's supposed to, then it must also be the case that the interval from negative infinity to infinity encompasses the entirety of the real numbers. And this is something that we could show by subset inclusion. That's normally how we show the two sets are equal to each other. But instead, I want to rely on an argument very similar to what we were looking at earlier. Let's pick two real numbers, a and b, with a less than b. It really doesn't matter what numbers we pick. You could pick a couple of specific numbers for the case of this proof if you want to. We could set a as -1, we could set b as +1, and the proof would still work out exactly the same. All right. So, having created that, let's take a look at this interval from a to infinity and this interval from -infinity to b. And what would happen if we took the union of these two sets? Well, we'd have -infinity to b union with a to infinity, which we could draw out on number lines the same way we did on that previous proof. The interval from a to infinity looks like that. The interval from infinity to b looks like that. And if we take the union, we take the idea of where they overlap, that should give us the entire real line. But based on what we were just talking about, if you take the union of two overlapping intervals, you should get the interval from the outside coordinates. So the outside of the first one is -infinity, the outside of the second one is +infinity. And to ensure that those really nice properties of intervals work, we want to insist that this conclusion also holds true. Once again, we'll be revisiting this idea in a couple of weeks when we get a more formal idea of the definition of bounded that will allow us to really investigate these properties in depth. But for right now, just remembering that this is a thing that you have seen before and something that is kind of useful. Ending our discussion of intervals, the value of interval notation is it's a nice condensed way to talk about the set of all values of x that satisfy an inequality. So I'd like you to take a look at a couple of quick inequalities here. How about 3x plus 5 is greater than or equal to 14? And how about 9 minus 2x is greater than 21? Right, the actual solving of these inequalities, hopefully not too bad at this point. But the interesting thing that I want you to think about before we move onward is how would you write the solution set to each of these inequalities in interval notation? If you're feeling ambitious, go back to the problem that we looked at in the last video, the three-piece inequality I asked you to solve, and write the solution for that one in interval notation as well. So take a few minutes to write out your solution to these two problems, and I'll see you in the next video.